Now in this section, we'll be looking at the basic properties of a Bernoulli process. And to do this, we'll set some assumptions. And we'll say, first off, that let's assume that we have n individual time slots, and that within those n time slots, we have S arrivals or successes. Just think of S as successes. So another way to say that is, let's say I have 30 discrete time buckets, and within those 30 discrete time buckets, I'm going to have a certain number of successes. And at the end, maybe 3 of those time buckets were a success, and I would say that S is equal to 3. Now, let's go ahead and put some definitions to this. And the first one is that we'll say S is just equal to x sub 1 added to all of the other x sub i's up to x sub n. And we can do this because we've defined this random variable x sub I as having a value of either 0 or 1. Again, that's saying that our x sub I must be equal to something in the set 0 or 1. And if it's a success, then we get a 1. And if it's a failure, then we get a 0. So with this, we can very easily come back and say that because of this, I can just add up all of my x sub i's, and from that, get the total number of successes, because a success is going to return a 1, a failure is going to return a 0. The next thing that we'll look at is the probability that our S, the number of successes, is equal to some specific value k. So let's say that over the course of all of my time slots, over all of my Bernoulli process, I want to know the probability that I have 3 successes in that time. So this would be the probability then that S is equal to 3, for instance. And so we can look at that as n choose k, so again, the number of combinations that would give us a number k successes out of n total time slots. We then multiply that by p raised to the kth. We're looking for the probability of success to the kth power, and then multiply that by 1 minus p to the n minus k. Again, this is the probability of failure raised to the power of the number of failures. And so again, this is a pretty simple formula to look at, but this is the formula that we can use to determine the probability of k successes in a Bernoulli process with n time slots. The next question we might ask is, what's the expected value of S? And we can say that the expected value of S is really just NP, n times p. And we get this from looking at the definition of the Bernoulli random variable, where we said the expected value of any random variable is just p. And so therefore, when we have n time slots, we just multiply the expected value of each individual random variable by that number n in order to get our expected value. Finally, the variance of our value S, the number of successes, is just equal to n multiplied by p times 1 minus p. Again, the variance of a single Bernoulli random variable is p times 1 minus p, and so we multiply that by n because of the n time slots. Now, another variable that we might be interested in as part of this Bernoulli process is the variable t sub 1, where t sub 1 is ultimately the time until the first arrival. And another way to look at that is saying, what is the minimum value of I, where the ith random variable is equal to 1. So in a given Bernoulli process, you may have multiple 1s that occur, but what is the minimum value that occurred in a specific set? So this is kind of using that second approach to processes, stochastic processes that we looked at, where we say that the sample space is just all possible sets as an outcome, and we're saying what is the minimum I that gives us x sub I equal to 1. Again, just the time until our first success. Now we can go ahead and expand that, and we'll find that this is the probability that t sub 1 is equal to k, where k, again, is just the kth iteration, right? We're saying what is the probability that the first arrival is a specific iteration, and we'll call that k. And from there, we can say that that is equal to the probability of k minus 1 zeros followed by a 1. So it's just, again, the set 0, 0, 0, 0, all the way up until you get to a 1, where 1 is in the kth time slot. From that, we can find that the probability of this is really just 1 minus p to the k minus 1. So I need that many zeros multiplied by p. And we don't have to worry about n choose k because there's only one specific pattern in which this would occur, and that is, or only one specific pattern we care about where this could occur, and that is all of zeros and then a 1. Now, you may recognize this formula right here, this 1 minus p to the k minus 1 multiplied by p, and recognize that this is just the geometric distribution, something that we've also covered as a random variable. So given that this is a geometric distribution, we can then actually just pull the expected value and variance straight from our definition of expected value and variance for a geometric random variable. And we would find that the expected value of t sub 1 is just 1 over p, and that the variance of t sub 1 is 1 minus p divided by p squared. And again, these pull straight from our definitions of a geometric random variable that we covered back in our discussion of discrete random variables.